This is a lesson on the wave nature of light in a unit on light and optics. The first thing I have for us is to review some properties of electromagnetic waves, which I've gone over in prior lessons. They're composed of mutually inducing electric and magnetic fields that oscillate in phase through a vacuum. And we can see that in the picture over here. Here's the electric field and the magnetic field. They oscillate in simple harmonic motion through time in the direction of the wave travel. And so we know the speed of light is here. It's derived by Maxwell's equations. Their electric field and the magnetic field are related to the speed of light, and their vector orientations have restrictions as well. The medium affects the propagation. Light gets slowed down in a medium, and we saw that in refraction. Because light is a wave, we see that it exhibits all classical properties of simple harmonic oscillatory waves. And in particular, we'll be keeping with us the wavelength. As we move forward, we've been looking at the wavelength. We'll also remember that waves carry energy. A light wave carries a specific type of energy in the electric field and the magnetic field of that wave. So we can relate the intensity to the actual value of those electric and magnetic fields. As we head towards studying light more as a wave, I wanted to talk about the idea of plane waves. Plane waves are waves whose wave fronts are uniform in amplitude and parallel to one another through space. And you can see that over here in this diagram. I really like this one because it's a 3D view. You can see it from the top or from the side here, but it really shows that all the wave is equal in amplitude and that these wave fronts are parallel to one another. And so it's just a continuous wave that oscillates through space, and it's very uniform in certain ways. We can see that up here in the refraction picture that I drug along from Hewitt, is that there is wave fronts here. When it enters another medium, those wave fronts change direction, but they're all parallel to one another. All of the wave fronts are separated by the wavelength. Because it's a simple harmonic oscillatory wave, there will be a wavelength here. As we move forward with light, another few terms that I wanted to throw in here so you knew is monochromatic. Monochromatic means one color, and what we're going to assume is that light has one wavelength only. It will be given one. So when I look at waves interfering or doing anything in there, there's only one wavelength. There will be a point where we will look at white light, and just to remind you that white light contains all of the wavelengths, especially of the visible spectrum. So as we're letting these plane waves move through space, what we need to consider is how they were created. How do we get a plane wave? And what happens when they encounter obstacles? And so a fundamental principle as we're looking at waves, and this is true for all waves, not just light, is Huygens' principle, which says every point on a wavefront is a source of wavelets that spread out spherically in the forward motion at the same speed as the wave itself. And I put two examples here from the two different textbooks. Hewitt had a picture of a spherical wavefront, and OpenStax had a picture of a planar wavefront. We can see that it's just a straight plane through space. You can see all along here they've chosen some dots to be sources of wavefronts, and that's what this says. Every point on a wavefront is a source of wavelets. So all along here, every point along this wavefront is a source of a bunch of waves. Spherical waves can emanate out from all of these points. And what happens is, through interference and the symmetry that happens, all of those wavelets that are spherical, they interfere with one another and they add up to another plane wave. So as this wave moves forward, it will continue to be a plane wave, whether it's planar in shape or spherical in shape. The waves spread out as they encounter obstacles. So you can see that's how we get a plane wave, is it kind of interferes with itself. But then when it encounters obstacles, this principle of Huygens really shows us that how waves bend around obstacles. So what do I mean by that? This is an occurrence we call diffraction, the bending of light around edges of an opening or other obstacle. And so I have real water waves down here. This is a picture of a real water wave. You can set up a wave tank and have an oscillator create a bunch of waves just back and forth at a consistent frequency. And you can see here that the size of the opening has changed, and that kind of changes the pattern. But we see the spreading here. When this wave comes in, it doesn't just go straight through. It spreads out into the regions on the side. And that's what we call diffraction. And it is driven by the Huygens principle, where each wavefront becomes a spherical source of waves. And so we get the spreading out. And there's different spreading out according to different wavelengths or obstacle sizes. I wanted to show you this picture over here. This has sound waves in it. If there is some sort of speaker sound out in this region here, the sound goes through the door, this is a door, through this opening, and a person outside of this region here can hear the sound because it diffracts out into that region. So we see it happens with sound waves, we see it happens with water waves, it also happens with light waves. And these different types of waves have different wavelengths, different medium, of course, but different wavelengths and frequencies. And so when we look at the size of the wavelength, the size of that wave compared to the obstacle or opening that it moves through, that is a significant effect, a significant factor. So the size of the obstacle compared to the wavelength. Here we have some pretty wide waves. They go around a pretty large object, and we can see that there's some diffraction into this area. So a wider wave will diffract at a larger angle. We see if we kind of change that obstacle, we have a little bit less diffraction, but it will diffract into this area behind that obstacle, and there will continue to be a wave. So then you see that the wavelength changes. We have the same obstacle, but different wavelength. So when the wavelength is much smaller than the obstacle, you get much more defined edges along this, what I will call a shadow, right? You can have a shadow in here. There's sort of a shadow for the wave. So there's much more defined lines of the shadow, and there's not diffraction into this area. So smaller waves will not diffract at very large angles at all. And I have this picture up here. It was sort of part of what was on the previous page, where I had sound here. Over here there's light, and what they are exemplifying is the difference of the wavelength. Here it's the same door, the same opening. When I have sound go into a room, we can see that the sound fills out to the sides, to the corners of the room. But when there's a smaller wavelength, with light there's a teeny tiny wavelength, right? Nanometers is visible light. We get a very distinct edge along these shadows with the diffraction. So the light will kind of make it in this area, but not very bright at all, not much light at all. As opposed to sound, it'll still be just as loud here as it is here generally. Because that wave is freer to diffract, it has a larger wavelength. So those are factors that affect diffraction, and you will see that in questions and as we move forward into further lessons.